In this video, I'm going to describe the major components of the two critiquing practices. Before I begin, I would like to again note that the descriptions provided of the NGSS science and engineering practices are based on the book, Helping Students Make Sense of the World Using the Next Generation Science and Engineering Practices, released in 2017 by NSCA Press. The critiquing practices include engaging in argument from evidence and obtaining, evaluating, communicating information. Argumentation has been categorized as a critiquing practice because students critique arguments from peers and other sources by citing relevant evidence, or comparing and critiquing two arguments based on the quality of their evidence and reasoning. Obtaining, evaluating, and communicating information is a critiquing practice because scientific information needs to be critically evaluated and persuasively communicated from evidence and information gathered. As stated previously, the critiquing practices are iterative and can occur at any point in an investigation. Let's cover the first critiquing practice, engaging in argument from evidence, which is listed as the seventh science and engineering practice. In a general context, an argument typically means disagreement. However, in the scientific community, argumentation is a process of producing and critiquing knowledge when unsure of the ideas being constructed. Through the process of argumentation, students develop more confidence in their ideas through making and supporting claims, evaluating one another's ideas, and working towards reconciling their differences. An argument reflects the student's ideas as well as the supporting evidence and the critiques of the alternative arguments. This can occur as a verbal exchange or formally in writing. Argumentation is not a standalone practice. Argumentation seems to occur often while constructing explanations, but argumentation can occur alongside all 7 of the other practices. For example, students may engage in argumentation while planning and carrying out investigations if they have different ideas about the protocol, or during data analysis if the students have different interpretations of the data, or even when developing the most appropriate model to explore a phenomenon. To distinguish the practice of argumentation from simply providing an explanation, 3 components have been identified to characterize a scientific argument. First, students must identify a supported claim. Teachers can facilitate this process on eliciting pieces of evidence from students to support their ideas. For example, if a group of elementary students are observing caterpillars on milkweed and notice that the milkweed is disappearing from the cage, they may engage in argumentation to determine what is happening with the milkweed. Students can use data they collected as evidence or a disciplinary core idea that supports their claim about a particular phenomenon. For example, the students may make qualitative observations about caterpillar feces in the cage. Other students may observe the teacher remove damaged, dried up milkweed from the cage every so often and provide an alternative claim that the teacher is making the milkweed disappear. These are both types of evidence that can be used to support the student's claims. After our students have made a claim, they should evaluate and critique claims to identify strengths and expose weaknesses. This could occur with their own claim or the claims of others through argumentative interaction. Evaluating the scientific arguments of others and presenting counter-arguments is an important process of science. Continuing on with the example of the elementary students, when the students present their claims to one another, they may provide a counter-argument to the claim that the teacher is removing the milkweed from the cage by explaining that the caterpillars are eating the milkweed and it is going into the caterpillar's stomachs. The fecal matter is evidence that the caterpillars are passing a long ways from the milkweed. Finally, if there are multiple claims being discussed, the students must go through a reconciliation process to revise and prescribe to a particular claim. This doesn't mean that all students will be convinced of one single claim. However, the reconciliation process allows students to further evaluate claims and explore the content of each claim. For example, the student that thought the teacher was removing the milkweed might still think that is part of how the milkweed is disappearing from the cage, but the caterpillar is eating the milkweed seems like a plausible explanation after he considers his own body's process of eating and digestion. In terms of argumentation, there is progress towards reconciliation, rather than an absolute agreement upon one single right answer. Argumentation has an everyday meaning that is not consistent with the process of scientific argumentation. So it helps to clarify what we mean by the process of argumentation. As stated previously, argumentation does not require disagreement. Students are working together to construct knowledge. Arguments are not simply a process through which explanations are created. Argumentation is both a process and a product. The process entails critiquing the claim by evaluating the evidence, and reconciliation leads to the presentation of a final argument, the product. Although argumentation may seem easier to facilitate around phenomena that don't have a definitive answer, it is important to engage students in argumentation around issues that have one correct answer. This allows the students to dive deeper into the content and develop a richer understanding. As stated previously, argumentation does not necessarily require the construction of an explanation. Although they are often seen together, these are two separate practices. Argumentation can occur with any of the other 7 practices. We have looked into what scientific argumentation looks like, but we must point out what does not align with the NGSS vision of the argumentation practice. First, arguing about a black box problem or some socio-scientific question that motivates students to support their claims using information about social aspects of the situation are not examples of the NGSS vision of scientific argumentation. Students learn some of the discourse moves for argumentation from doing this, but they are not constructing knowledge about scientific content. For example, if a teacher poses a question about the student's opinions of genetic testing, the students may have an idea of how the process occurs, but the formulation of their opinion is not furthering the scientific understanding. Second, student presentations do not support the vision of scientific argumentation because the presentation is typically meant for the students to demonstrate their mastery of the content. They are not evaluating, challenging, or learning from one another's ideas. Finally, it was previously stated that students can construct arguments around ideas that have one correct answer, but if there is a clear answer that is the only correct one, the students probably will not come up with different ideas, and the class will easily be confident about a single claim. This provides little need for students to attend to each other's ideas and provides little need for the students to defend their ideas. So how can we support this practice? Argumentation is an important practice because it gives students the chance to present their ideas, and oftentimes the best ideas emerge as students counter-argue, compare, and evaluate their claims. However, the teacher must take care to appropriately facilitate the practice of argumentation so that it doesn't turn into an uncomfortable situation with students attacking one another's ideas. Teachers can overcome this issue if there are multiple ways and opportunities for students to engage in argumentation. For example, providing opportunities for students to construct ideas on their own, then share them out in a small group for reconciliation before sharing them with the class, provides a barrier for the individual's ideas. Also, the teacher must explicitly and repeatedly discuss the norms and expectations of scientific argumentation. For example, the teacher can point out the effectiveness of the evidence rather than whether or not their claim is completely accurate, which can be fleshed out as the reconciliation process occurs. This shift in focus provides an opportunity for students to construct knowledge. Additionally, the teacher can model the types of questions students should ask one another as they evaluate each other's claims, such as, what evidence do you have? And what could be some other possible claims and the evidence for those claims? All in all, there is a lot of variation to the practice of argumentation, but it is a practice that can be incorporated into the classroom at varying levels of intensity to develop students that are active participants in understanding scientific content rather than passive recipients of factual information. The second critiquing practice is obtaining, evaluating, and communicating information. Within each of the disciplinary core ideas, students are expected to carry out this practice as it relates to the science and engineering ideas that they are learning. This practice entails students gathering, critically examining, and communicating their sense-making about the natural and designed world. This is one of the most heavily used practices of scientists and engineers. In fact, over half of their time is dedicated to this practice. Not surprisingly, this practice is very diverse and ubiquitous. The first component of this practice is obtaining information. Students can do this through internet searches, text-based sources, interviews, or visual representations such as graphs and diagrams. Gathering information is typically done at the beginning of an investigation. However, it must be noted that this practice is not necessarily linear. Scientists and therefore students may need to obtain information about the phenomenon under study at any point in the process. Students should be able to obtain information from a variety of sources. As students enter high school, they should begin to obtain information from scientific-specific databases. They should also have the opportunity to read technical literature. Although most of the time, if we teach older students, we assume that they know how to obtain information, there are some possible learner challenges that occur with this practice. Students may not always know where it is best to search for technical information. Also, students do not know what keywords to search for when they are looking for specific information. When it comes to accessing technical information, students don't always know what the most helpful resources are because they're unfamiliar with technical literature. When students begin to explore technical research literature, teachers must provide scaffolding to make these resources accessible to their students. Listed here are the strategies that can help the teacher walk the students through this process. To help students focus their reading in an expository text, the teacher can provide guiding questions to help students identify the target information. After the students are comfortable in identifying where they can locate important information, the teacher can have the students create learning logs so they can practice identifying main concepts on their own. For example, encouraging students to read the introduction and discussion of a journal article to find the most pertinent information to understand the findings of a study. It is also helpful to provide students with graphic organizers or help the students learn how to make them on their own and encourage them to annotate the text as they work through the information. In addition to simply interpreting these difficult texts, the teacher can encourage students to focus on the writing style of the journal articles to help shape the communication of their own findings. This is often difficult for students because they are not used to writing in a concise scientific style. Students should be repeatedly engaged in reading and writing scientifically in order to increase the sophistication of the practice. The second component of this practice is to evaluate scientific information. This is an extremely important practice, especially recently as students have more access to information than ever before through the use of social media. A main goal of scientific literacy is to promote critical analysis of scientific writing to determine validity. Teachers can develop this practice by modeling the process of analyzing a resource for its credibility. Students should be given opportunities to determine credible sources from non-credible sources using the thought process modeled by their teachers. Like obtaining information, this is a practice that should be continually repeated. For this practice, there are some possible learner issues because students may have a hard time discerning credible scientific sources. The information may seem plausible, but that is because some sources know how to manipulate information to convince the general population. Teachers must be explicit in showing their students how to judge a credible source from a non-credible source. The third component of this practice is communicating scientific information. It is important that students are able to report findings to a wide variety of audiences. The teacher should model how the communication may change as the students report to different groups of people. For example, the way the students communicate their scientific findings to a technical audience, such as their teacher or other students in their class, would be different than the way they would communicate their findings with a non-technical audience, such as their parents. Students should be given ample opportunities to communicate their information in different ways, such as oral presentations, written lab reports, lab notebooks, visual representations such as graphs, and diagrams. They should also be able to determine when certain types of communication are more appropriate than others. With each of these ways to share information, the teacher should model how to communicate properly. For example, in a lab report, the students would write out all of their results as concisely as possible, but in their lab notebook, their results may be written as a series of tables, diagrams, and/or graphs and contain no verbal communication. One of the most important learner challenges that occurs with communication of scientific information is that students do not know how to give credit to the appropriate sources when reporting information. As a teacher, I saw this issue time and time again. Also, for many students, their high school science courses are the first time they are seeing EPA format, as most of them have been using MLA for their writing. Studying information is a skill that must be repeatedly addressed over the course of the year. One other possible challenge that is not listed here is the use of tables and graphs to communicate information. In the older grades, students are not used to doing investigative work, so the teacher needs to scaffold the type of information the students should be recording and communicating to support their conclusions. Although the practice of obtaining, evaluating, communicating information is an extremely broad practice, there are some distinctions from the general use of these terms. What is not intended by this practice? Students engaging in obtaining information that is not contextualized within the scope of their work is not part of this practice. For example, research papers on a topic of the student's choosing as an add-on assignment is not aligned with the NGSS practice of obtaining, evaluating, and communicating information. The information that the students are obtaining must be an essential part of what they are doing in class. Also, rote memorization of scientific terminology that is not an essential part of the work the students are doing is not aligned with this practice. That is not to say that this type of work is not sometimes necessary, but it is not a task situated in the larger context of investigative and communicative practices. Scientific language takes on a deeper meaning when the students are engaged in using the language in the context of the phenomenon it describes. Beyond its use in the science classroom, this practice is useful in many facets of the student's life. So repeated intentional engagement in this practice is essential for students. The NSCA book provides useful resources for promoting scientific literacy on page 265 and throughout chapter 12 in this book. The critiquing practices allow students to extend their thinking through considering evidence, defending their claims, and evaluating the information of others.